let's start. I hope this is the right one. Yes. Okay. So we have pretty much covered the battle problem, I think. So we have done these things. And then we now want to also continue to look at this out of equilibrium problem. The battle problem is also an out of equilibrium problem. I'll touch upon this relatively simple equation, the diffusion equation. I don't know why we study the diffusion equation, because the idea of studying diffusion, if there is an equilibrium state, has already been addressed by us when we studied the velocity autocorrelation function. You may recall that the integral of the velocity autocorrelation function gives you the diffusion constant. I discussed this in class. I'll show you a fairly long time ago, though. It was probably even before that. I wish I could pick up an index and get there quickly. Maybe here, around here. If you integrate this velocity autocorrelation function over time, this is what you got. So slide 71, which was almost in the past ice age, we had figured out that the diffusion coefficient or diffusion constant is nothing but the integral of the velocity autocorrelation function. The velocity autocorrelation function gave us information about, you had a system, you perturbed something in the system, the perturbation propagated throughout the system, and the system eventually returned to an equilibrium state. So velocity autocorrelation function gave us the detailed journeys information about this jth particle as it went from the perturbed state at t equal to 0 to the equilibrium state at t going to infinity. That's why the integral is from 0 to infinity. So that gave us the diffusion coefficient. This diffusion coefficient is a diffusion coefficient that is associated with the return to equilibrium. But what if there is no equilibrium? You can take a cup of water and you can drop some ink in it. And we all know what happens, right? The ink basically diffuses not only at the surface, but also at the bulk. It's a very complicated three-dimensional diffusion problem. And that diffusion may eventually take you to equilibrium, in which case you might get a D that is comparable to this T, but there is no guarantee of that. So the diffusion equation is the more general picture, but it is also what we would call a phenomenological problem. It is not a Hamiltonian problem, not a problem where we can go down to the Hamiltonian and say, look, this is the potential under which we are studying, and we are looking at this diffusion coefficient. That is not automatically put into this problem here. So the diffusion equation, therefore, is not on the menu every time a non-equilibrium or a nonlinear course is taught. It's a matter of choice. I just threw it in because I thought I should at least let you see it. And then If you find it important at any point in your research, in your study, you can use the idea and build on it on yourself. So here, again, that ink spreading is the context given. So what am I doing? Draw. So you see, this thing is called Fick's law. Fick's law has to do with how this diffusion coefficient behaves. And in this case, it is the density, some kind of a density as a function of space and time of the ink drop itself. And the whole idea of diffusion starts from conservation of matter. So basically, conservation of matter results in material never disappears. Whatever it is that's there, it's going to be there. So del rho del t, which is how the density will fall, is connected with the divergence of the current in this case. In this case, the current meaning the amount of ink that is moving out in time in various directions. So divergence of J is negative of del rho del t. That's what it is. So this J, this current J, one can think of it as flux of this substance per unit area, per unit time, how much is flowing out. And that can be described more formally, this current, as the negative of diffusion constant d times delta of rho, gradient of rho. Rho is a scalar, so how rho is falling is a function of space. So that's my current vector, if you will. And the divergence of the current vector is what del rho del t is. So it is very interesting then that when you look at this divergence of J, there is no information about how J is connected to rho here, because J is being introduced as a current. And it is here that you are connecting the J, which is the current, with how rho is falling, rho is changing over space, del rho del x, d rho dx. In 1D, it's 0 dx. In 3D, it's divergence of rho. They are dimensionally fine. I mean, I've shown the dimension here. As I said, J is amount of material. This is area. This is time. And we know what density is. Density here is going to be m over volume. And then divergence will give you a 1 over L because it's a del del x. And then you have to have the diffusion coefficient with this dimension, length squared over time. The diffusion coefficient is actually a very interesting quantity. For example, you can see the diffusion coefficient can vary over many, many decades in nature. How animals diffuse, for example, on a landform. If you're going to some national wildlife park in Africa and some other country, you know that these animals move around and come together, so there's diffusion processes going on. Especially if you measure that from high above, you can look at this as a large-scale diffusion problem. Similarly, when you have a bacteria that is getting inside your body, let's say it's in a liquid type environment, fluid type environment, then this bacteria is going to swim. So swimming of bacteria or swimming of live things also is a diffusion problem. And in fact, it is a diffusion problem of great interest in the current times, because movement of these kinds of live entities comes under the study of what is called active matter. In fact, the whole statistical mechanics of active matter has been developing for the past 15, 20 years at most. And one of the pioneers of this field is our good friend at IISc that Vivek may have met, Sriram Ramaswamy. Sriram started this working in this field many, many years ago with John Toner, who was at Oregon. And over the course of time, the field got established. And of course, he's a household name almost because of his contribution to active matter work. So anyway, so you can see that the diffusion problem, the reason why I picked the diffusion problem is because parts of it are tied to very exciting current modern science. In this case, biological physics, statistical physics, soft matter physics. It goes under all these names. Soft matter is a very in term, so to speak, in terms of describing this. So now the question is that you have this equation, you have this del rho del t plus divergence of J equation, where divergence of where J itself is like a gradient of rho. And if you put these equations together, what happens is you get the diffusion equation. And the diffusion equation is basically, diffusion equation is this equation here. You see on both sides of the equation, you have density. And that is the diffusion equation. Del rho del t equals d del square of rho. You see the way this equation is set up, del square of rho is where all the physics of how rho is moving through the fluid is captured. But the equation as such doesn't give you any way of digging into how this rho is moving through the liquid. So this is one of the sort of interesting features of this particular equation. I won't get into this issue about what kind of an equation it is, elliptic versus parabolic and so on. But I would like to point out something which is structurally important. If you look at the left side of the equation, it's a first derivative in time. If you look at the right side of the equation, it's a second derivative in space. An equation which is second derivative in time is robust under a t going to minus t transformation. But an equation that is a first derivative equation in time will flip sign under a t going to minus t transformation. So therefore, the fact that there is a first derivative in time in a differential equation, not an integral differential equation, in a differential equation implies that the equation introduces irreversibility in time in the system. Because del rho del t is first order. And if you flip t, the equation will change. You can't let that happen. So the physics therefore requires that this be described as an irreversible process. Now herein there are a lot of interesting things. For example, when we showed that diffusion coefficient as an integral of velocity autocorrelation function, that, by the way, is reversible in time. Because Newtonian laws are reversible in time. This, on the other hand, is irreversible in time. So there are, therefore, all these details in the problem that we need to keep in mind. But I need to check this, but as far as I know, the d there and the d here pretty much mean the same thing. So there is a sort of aspect of this irreversible in time equation being introduced as a quote unquote coarse-grained equation. Coarse-grained meaning there's an equation that is drawn out for larger scales. It's not an equation with microscopic details of physics in it. If you put the microscopic details of physics in it, then of course you won't quite get exactly this equation. You will get the kind of D that we talked about, especially if there is equilibrium in the system. This, on the other hand, may or may not lead to equilibrium as far as I know. I'm not an expert, unfortunately. I wish I was on the diffusion equation problem because I've never really worked on it. So I don't know the nuances of diffusion too well, but I'm only sharing with you stuff I know. One way to approach this diffusion problem uh, relatively quickly without getting uh, tangled up into issue of potential and interaction, structure of the molecules, structure of the fluid type details, is by essentially considering uh, random walk of an object uh, on in space. It can be a random walk in 1D, random walk in 2D, which would be obviously infinitely more complicated, or random walk in 3D and so on. In general, random walk in D dimensions. So here you start at 0 in this diagram. You start here, uh, and then you have a chance of going to the left and an equal amount of chance of going to the right. You do a coin toss and decide. And so you can go to the left, and then the next step you can come back, or you can go to the left, and the next step you can go forward, then come back, then go forward. All of these possibilities exist. So everything depends then on the probability. So in other words, we have just replaced this density here, which is mass over volume, right? Density is mass over volume. We have just replaced this density by a probability, or a probability density, if you will. So there's a slight change in how we are now looking at things, but physically things seem fine. Density is a dynamical quantity. Density is changing, obviously, and here we are modeling that changing with a probability of a random walker to go in this direction or that direction. There's nothing wrong with that, but there is a little bit of difference, if you will, between solving this problem directly and this problem here. So anyway, lambda is the average rate at which the jumps occur on the left and right. There's a time scale here. So how does the probability of being at site j at time t change as a function of time? That depends upon this average rate at which jumps occur, so lambda. The equation here on the right side is exactly same as a harmonic oscillator equation almost. You basically are doing pj plus 1t, that means moving to the right, minus pj of t, that means moving to the left. Remember the Chapman-Kolmogorov problem? It's the same idea. Going to the right has a certain probability, going back has a certain probability. Hopefully the probability going to the right is a little more than that of going back, because otherwise everything will continuously go nowhere. So here, the probabilities may not all be exactly the same, or maybe same. You'll still move one direction or the other, but eventually you'll be just going around if the probability is exactly the same. So anyway, so pj plus 1t. Similarly, if you go to pj minus 1t minus pj of t, that's why there are two pj's that are negative, and pj plus 1 and pj minus 1 are positive. This takes you here. So this is what we had. This is what we had from last page. And then what you do is you introduce this a, where this a is the lattice constant. A is the lattice constant. And lambda we had in the last page, this lambda, which is the average rate at which jumps occur. This one, this guy here, average rate at which jumps occur. So average rate means 1 over lambda is a frequency. So once you go here it says 1 over lambda is that frequency. So lambda goes to infinity. That means average rate of jump becomes very large. 1 over lambda goes to 0, which is the mean time between jumps. Or did I say it wrong? Lambda is the average rate at which jumps occur. So if average rate at which jumps occur becomes very large, then the frequency diverges, obviously. Frequency. What the hell am I saying? If lambda goes to infinity, average rate at which jumps occur is very fast. So 1 over lambda, therefore, is a residence time. That was the mistake I was making. So this 1 over lambda is the residence time. So the mean time between jumps, this is the residence time. How long it stays on the site. That's what it is. Okay, let me erase this. Now one can think about j times a. J, of course, is the site label, and a is the lattice constant, as this continuous variable x. So, and p is, as I said, the probability density, right? So you have the continuous variable x and the probability density. So then what we are going to do is, instead of writing pj plus 1t minus pj of t minus pj of t minus pj minus 1 of t, this is what I was telling you, just like in a harmonic oscillator equation of motion, this one. We do two things. We introduce an a, which is the lattice constant above and below. Basically, they cancel out. Then what we do is, instead of 1, which is essentially the lattice constant, we call it a. So j now becomes, instead of j times 1, ja. So ja plus a minus p of j comma t, and so on. And because now this is a rate that you have to measure, it is divided by the lattice constant a here explicitly and by a here, and then you divide the whole thing by a. So in other words, you are now writing in effect the double derivative that you have. You see, the double derivative expression was very simplistic in this version, or even in this version, because the lattice spacing was 1. So we didn't have to worry about what division by the lattice spacing is happening, because it is the division by lattice spacing that takes care of the right side of this equation of motion. Right side of this equation of motion is your del square of rho, right? If you go back here, it's your del square of rho in this part. So this is your del square of rho, but once we set up this equation, there is no real mention of this del square. We are just saying probability of going to the left, probability of going to the right, and not saying anything else. Well, implicit here is the division by the lattice spacing. Because imagine if the lattice spacing is not the same, then all this right side will be affected. So because we set it to 1, how do we set it to 1? Well, that 1, oops, that 1 is right here, right? What happened? Oh, I can't do this. Okay. There's something has gone off. Anyway, forget it. So basically this 1 is implicitly the lattice constant here. And once you write it up in terms of a, even for purposes of dimensional correctness, you have to make sure that the length square enters. So that's why you divide each of these processes by a and divide the whole process by a. So it's 1 over a times 1 over a. That's why there is an a square here. So this a square is to take care of these two a's here. And that a and that a. So in other words, everything works out at the end, excepting that d is now written as this quantity, 1/2 lambda a square, where lambda goes to infinity, a goes to 0. So d is now given form. The form has to do with the lattice constant, and the form has to do with this rate. Lambda 1 over lambda is the mean time between jumps. So this is the mean residence time. Sorry, I'm always getting confused. Mean time between jumps. That is a measure of the residence time. So we describe lambda, therefore, as average rate at which jumps occur. So therefore, it's the rate. So this is your D, and then this is your probability equation. So instead of writing it in terms of rho, we have written it in terms of probability. So now this problem can be done a little bit further, but essentially the next part of this problem is to actually try and directly solve this equation that we have. How directly can we solve this equation? That's the problem. In physics, I think that you may have seen enough of this by now, hopefully. When you are dealing with partial differential equations, it is not uncommon to see if you can do a transform and simplify your work. It can be a Fourier transform. It can be a Laplace transform. It can be other transforms. There's the Mellon transform. There are many, many transforms. And the difference between physicists and engineers typically, especially when we are students, is that engineers know a heck of a lot more about transforms than we physicists do, right? So the standard trick when you look at a problem is to see if you can reduce it to an algebraic problem, because algebraic problems are somewhat easier and you have a lot of linear algebra machinery that may be available. So that's kind of what we do here. We set up some simple boundary conditions. We say as r goes to infinity, on the left side or on the right side, so plus infinity or minus infinity, the probability of finding a particle there goes to 0. In other words, it is contained in space, right? That's what we are saying. Yeah, Tony.
Use the bathroom real quick and be back in 90 seconds.
You want us to stop for 90 seconds?
Yes, I'll be right back.
Yeah, no problem. Yeah.
Thank you so much.
We'll wait, yeah. So Vivek, you can see here that we are going to try and do a Laplace transform. And then we are also going to follow up with a Fourier transform. So, and see what happens.
Yeah, me and Mukesh sir, kinda we did this in our first semester of coursework.
I see.
Yeah.
Laplace transform and all these transforms. There is a very,
Yeah.
very nice book. Let me tell you what the name of the book is. It's called, I probably have this book. I have it. It's called Operational Mathematics by Ruel B. Churchill. It's an old book. I have the book. Let me see. This is my ancient copy. You can see here. Operational Mathematics by Ruel Churchill here. And it was published by McGraw-Hill. I have the third edition from the time when I was a student, so this is old. This edition is from 1972. There may be newer editions. So McGraw-Hill. A very, very nice resource to have. I was telling Vivek, Tony, that transform mathematics is captured very nicely in this book, which is like a graduate level text in math physics, operational mathematics. In fact, this was my text actually. And I was very lucky to have a very nice mathematical physicist as my professor who taught me mathematical physics. This is not always the case. Usually you'll get a theoretician or sometimes even a very good experimentalist to teach you mathematical physics. Nothing wrong with that. But this guy, Bill Bird was his name, B-Y-R-D, Bill Bird. He taught us mathematical physics. And the course was very interestingly directed almost entirely on learning to do operational mathematics. Certainly a good part of it. I mean, all the problems are given here in terms of mathematical physics problems, but the emphasis was on this. So anyway, just if you want, if you can catch a PDF, I'd strongly encourage you to have it around because it comes in very handy. So anyway, so now what happens is that you take the Laplace transform of P of RT, the probability density, and then it becomes P tilde. And the Laplace transform is not on the space. The Laplace transform, as usual, is with time. So T, therefore, is going over to S. So T is going over to S. This is where the Laplace transform has been done. So Laplace transform of the original equation del P del T RT equals D del square P yields this equation here. So just to remind you, if you don't know, Laplace transform of a derivative gives you this structure here. So as you can see, T has gone over to S, and then the Laplace transform of P tilde of R and S. So this is the first term, and the second term is minus of P R0. This is the old P. This is not the P tilde. This is the old P. This is the probability density itself. That is the initial condition. And then on the right side, you have D del square of P tilde RS, because this is generic. But keep in mind how Laplace transform of derivative terms are taken. And that's what enters here, Laplace transform of the derivative term. Del P del T, that's S P tilde minus original P of R0. The reason why this is so is because it is basically a definite integral that you're doing. 0 to infinity acts as a definite integral. Yes, Tony.
Uppercase P tilde and lowercase P tilde, the same thing here.
Uppercase doesn't have a, oh, you're right. What the hell is this? Yeah, this is a lower, this should be lowercase.
Okay.
It is my, I didn't catch this thing. It should be like this. Good point. Good catch, actually. So, yes. So now you can write S minus del square P tilde is the delta function, because the P of R and 0 is just that the particle exists at position R at 0 time. That's your initial condition. So therefore, you have this on the right side, which means that P tilde RS can be thought of as the following. P tilde RS is basically the Fourier transform of P tilde KS. So here you're doing e to the I k dot r, KS. So therefore, P tilde KS is the inverse Fourier transform of P tilde RS. So what have we done? We have essentially gone first from P of RT to P tilde RS. Then we have gone from P tilde RS to an inverse Fourier transform to P tilde KS. Now you can ask the question, what would have been the pros and cons of doing it the other way? You could have asked the question, what if I did a Fourier transform of S and T and the Laplace transform of R and K? You see, from a mathematical point of view, the transform mathematics is being used purely to get to a convenience point. There's nothing fundamentally changing. You are just changing the way you express it. It turns out, however, that this is the preferred route. The first one, which is S and T being a Laplace transform, is a preferred route than the other way around. Why? Because it turns out that if you do a Laplace transform of the space problem here, it becomes more challenging to do the other side. So this is the better way, is what I'm saying. Actually, if you look at Balakrishnan's book, I think he talks about it at some length. He does a lot more on this problem than I am doing. But that's a matter of choice. Anyway, so then it turns out that this S minus D of delta square, because P tilde Ks has this e to the minus ikr, it becomes S plus Tk squared P tilde K is equal to 1. And this is exactly the reason why doing it the opposite way is not very helpful. So doing it this way turns out to be easier because it gets you to an expression of P tilde Ks much faster. And the expression, of course, is very straightforward. Of course, you don't have a potential in this problem. So now the inverse Fourier transform of P tilde Ks is going to be a bit of a problem to do. So P of Kt, instead of doing a Fourier transform, you do a Laplace transform. And this Laplace transform finally gets you to P of Rt, okay? And if you work it out, that gets you to this form of the probability density function in time. It gets you to a Gaussian integral with the diffusion coefficient in the denominator of the exponent, the e to the minus whatever. And downstairs also, there is a diffusion coefficient times time explicitly entering. So, again, I want to remind you that this is just the probability density problem. This is not the rho problem. We have not done the rho problem. We have done the probability density problem here. The rho problem, on the other hand, gives you the same Gaussian distribution, but it doesn't give you the same denominator. The denominator turns out to be different. In fact, it is 1. And that problem is trivial to do. This problem is harder to do. You see, our original equation was del rho del t plus del rho del t was d del square of rho, right? Isn't that what it was? Or was it plus? This was minus d del. Oh no, this is not the original. This is the original equation. Del rho del t equal to d del square of rho. This is our original equation. This is the diffusion equation here. This fellow here is the diffusion equation. But we didn't solve rho. We solved for p. If you look at the diffusion equation, you see on the left side, it's a time derivative. On the right side, it's a space derivative, double derivative of space. So if you have derivatives that are different variables on two sides of the equation, that means you can write del rho del t equals d del square of rho equal to some constant, let's say lambda or something. Just like you do when you solve the Schrodinger equation or when you solve the Laplace equation and so on. Because left side has a time dependence, right side has a space dependence. So therefore, left side equal to right side equal to some constant. Then you can solve this problem. And if you can solve this problem, you'll find that you get a slightly different solution with appropriate boundary conditions. Here, I'll show it to you. I had it actually somewhere in my. I was just doing it using a simple AI set of questions. No, this is not the problem. What is this one? Ah, this one. Let me share this thing. Let's see if this works. You see it?
Mm-hmm.
So you see, this is our rho problem. And then I had given it two kinds of boundary conditions. One is an absorptive boundary condition where the particles gets absorbed when it reaches x equal to 0. And the other is a reflecting boundary condition, and the particle basically bounces back out when it's at L. You can, of course, make them both reflecting. In one case, it turns out to be a Dirichlet condition. Particle gets absorbed, the density disappears. And the other is a Neumann condition, where the first derivative, the variation of rho or u with x at x equal to L is 0, because it bounces around. Now, if you do that, you see, then you can write this equation in the following form. Just like you do for Schrodinger equation, just like you do for electrostatics equations and so on. Same form you can do. And then you can move it to a time component and to a space component. The time component is the one that gives you the same minus lambda squared dt on an exponent. Space component, this is going to give you a sinusoidal function, obviously. So therefore, if you impose the boundary conditions I gave, for example, then you end up with this solution. So that one is for probability density. This one is for something like a density function itself. And this one has the e to the minus d some constant squared t, just like there. But now you have all these harmonic terms that can enter because of boundary condition. So I thought about showing it to you guys also as part of this, but then I said, wait, I mean, you can just basically get it out of Googling. So what's the point in having a discussion on this? I just point out that this is the other way of doing the problem, but here you're doing the density problem. I just wanted to demarcate that you're not doing the density problem, you are doing the original, sorry, the probability density problem. Okay, let me stop sharing this and go back to sharing what I was sharing, which is this guy. Okay. All right. Anyway, so this is where we came, I think. And now you see this is the probability density. Almost the same structure, but now the denominator is different because the probability density, not a real density. Now, how is this integration done? I don't get into that, but it's worked out here, at least sketched out here. Essentially, you are doing this guy here, and the way it works is p of xt. If you go back here, p of xt, the left side, that is p of xt. D is equal to 1, so 1 over 2 pi only, not 1 over 2 pi raised to power d. And this is now your, what is it, the Fourier transform. going back. Yeah. So it's minus dt squared plus ikx. You're exactly doing this calculation for d equal to 1, this calculation. And in doing so, the problem boils down to completing this argument of the e as a square. And the moment you do it, which is this way here, you immediately get the Gaussian integral solved. So it is quite straightforward and it can be done. Now, let me not spend more time on the diffusion problem. The whole purpose of me touching upon the diffusion problem is to give you an idea that you can do phenomenological modeling of a diffusive process, and you can invoke rules of diffusion yourself as part of that phenomenological modeling problem and solve this equation to give it a behavioral form, how it should behave. Now, that may or may not agree with an experimental scenario because that would be dependent upon how good your model is. So if the random walk picture is inappropriate, it's not the best, then you will not get good agreement with experiment. If on the other hand, you have active matter with particular kind of directed motion, then you have to build in the physics of the directed motion into your right side of the diffusion equation. That you have to do. So I want to now just change gears. We are pretty low on time, but let's give it another 5 minutes or so. So we have not paid a great deal of attention to non-linear forces so far. A little bit we have done, but the non-linearity of processes we have not really worried about to a great extent. We have mostly, in fact, done rather linear problems or close to linear problems. But what about nonlinearity? What does nonlinearity get us? Why do we need to worry about it? These are very important questions. And these kind of questions were originally raised by Fermi when I briefly introduced the Fermi-Pasta-Ulam-Singo problem to you. I'll come back to this now. So one question I want to pose is we are often left with the impression, certainly in graduate level physics, that most of the problems that we need to worry about have linear forces or can be captured by understanding linear forces. We use the same ideas in quantum field theory, we use the same ideas in mechanics, we use the same idea in quantum mechanics in every field. We essentially reduce our problem in terms of harmonic oscillators. And then we quantize, second quantize, etc. as needed. And then we kind of give our students and us the impression that the nonlinear part is not important. If you really need to take care of that, then it's a special thing, advanced stuff, and so on. It's fundamental science. The answer is these are all completely wrong. And I wish we would stop doing that, but we have not reached that phase because science and teaching of science lags behind by at least 30 years at a minimum, sometimes way more, right? I think Jackson wrote his book on classical electrodynamics back in the 50s. In fact, the year might have been 1950. So, and we still use it. Anyway, so one issue I want to bring up is integrability versus non-integrability. Harmonic systems are integrable because you have quadratic potential, and a quadratic potential is always integrable. So therefore, harmonic systems are very integrable systems. Now, there are nonlinear equations that have emerged over time, and I'll soon show you some of them, that pertain to integrable systems. That means they can be directly integrated. And then there are those equations that cannot be directly integrated. See, integration is not a guaranteed process. Differentiation is. Integration may or may not be possible. So, question can be raised as to what do you mean by non-integrability? These are very deep philosophical questions. I mean non-integrability to be simply that the problem cannot be integrated using known tools that we have. So why should we study that? We should study it simply because it is important to study, because we don't know what the hell it is. We really don't. So I wanted to give you this quote, which I showed in the conference talk I gave that Vivek may have seen. Abraham Flexner was a very interesting character. Abraham Flexner, by the way, was one of the founders of the Institute of Advanced Study in Princeton back in the 1930s. And Flexner was a medical doctor. He was a very influential medical doctor. So when you go to the doctor today, the curriculum that your doctor got trained in all over the world pretty much, that curriculum was architected by none other than this fellow, Abraham Flexner. If the doctor is wrong, you can blame him. If the doctor is saving your life, you can thank him. But Abraham Flexner was a very interesting character. And he wrote something which you can find online. Is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the expansion of knowledge, extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though the fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. So the whole idea of pursuing something for the sake of understanding and pushing the boundaries of knowledge is very important. And while Flexner had a very sort of pragmatic side when he worked out the medical school curricula, he also had this very philosophical side where he really valued the importance of basic science, just asking questions without expectations, without a hypothesis in mind. So without getting into the formal structure of it, I want to go back to this integrability, non-integrability problem with which I came to Flexner. And part of the problem of what is integrable and what is non-integrable is captured in this theorem, which I won't do mathematically. I will just give you the spirit of it. It's called this Kolmogorov-Arnold-Moser theorem. Very important theorem. The message of this theorem is what is integrability and what is not non-integrability, but what is chaotic. What does chaos mean? Chaos is a very popular word, but what does it mean? So in an ideal world, starts with the solar system here. Planets move in perfect circles or perfect ellipses, let's say. We all know this is central forces, integrable problem. We can find the periods, we can find the ellipticity, we can find everything. So, but if you read it, the system is integrable, meaning its motion is perfectly periodic and predictable. In phase space, this motion lives on a torus or a donut. Each planet has a frequency omega. If you have two planets, their frequencies are, say, omega 1 and omega 2. The shape of motion depends on the ratio of omega 1 over omega 2, motion of both the planets. If omega 1 over omega 2 is m over n, where m and n are integers, then the biggest threat to stability is resonance, and resonance can occur when the frequencies are rational multiples of each other, like this. Imagine Mars is going around and Earth is going around, but their frequencies are rational multiples of each other. It can so happen that any kind of minor perturbation can throw this problem on into a chaotic state. And then the Earth and Mars's predictable motion becomes unpredictable. So question then becomes, what kind of setups are more stable? And the answer is that the ratio should be some highly irrational number. 3.14567, some irrational number, not a number like 3/5 or 4/7 or something like that, not a number where you have a ratio of integers. So this is basically the message of the Kolmogorov-Arnold-Moser theorem. It goes into big details depending upon which proof you look at, but the main point is that this ratio should be an irrational number, so there is no chance of any kind of quote-unquote resonance between these orbits that can throw it off. So when a system is non-integrable, usually this chaotic side, quote-unquote chaotic side, meaning that irrational, this rational number being m over n integer being a rational number being excluded comes in. So there are several proofs of it. It's okay. I mean, from a personal standpoint, my personal choice is it's not important to get into the proof of it. Just important to understand that what the Kolmogorov-Arnold-Moser theorem says, basically that a set of that irrational numbers give for a tougher thing in terms of stability. Let me kind of wrap up now. I want to just connect back to the study of waves, and we know waves are linear, but linear equations that gives us beautiful description of waves are unable to capture phenomena like this. This is an actual wave in the North Atlantic. It's about 60 feet high, and these kind of waves are very common actually in some parts of the world. And back in the 1400s and 1500s, when the ship traffic from Europe to the Americas was quite a bit, everybody wanted to come here. It was noted that a lot of the ships were getting lost. They were basically sinking. Now the ships were taken to be pretty robust, so why the ships were sinking was mysterious. But it turned out that one of the big problems was that we did not understand much about waves, and the waves that sunk the ships typically were these rogue waves. And here is a ship that actually got damaged by a rogue wave. That's actually documented. This particular event happened in the east coast of South Africa, where there is a current called the Agulhas current, which is very famous for having a lot of these rogue waves. And you can see these modern ships are typically not designed to withstand them. These waves can be easily 100 feet high, but ships are designed for 45 to 50 feet high waves. Here is a wave coming at you. Obviously, it means a lot of trouble. This guy obviously survived, so it was not a bad news after all. So all these people studied waves. All the names that you know Huygens' name from optics, he studied these waves. You know Newton's name from mechanics and all of that, he studied these waves. Taylor instability, Taylor studied them. Euler, Lagrange, Laplace, Fourier, Airy, Russell, Stokes, Earnshaw, Boussinesq, ultimately leading up to 1895 when this Korteweg-de Vries equation was solved, which I'll touch upon. So you see that our understanding of waves and nonlinear waves is actually tied to very applied problems, a mix of applied problems and fundamental science and Flexners questioned everything, try to understand things because you don't understand them, everything came to play. And that is what we have in front of us. Because when you look at wave equations and nonlinear wave equations, you're actually looking at some kind of a snapshot in time of the upshot of all these things that were happening not that far back, really, basically 150 years ago. And all these very important, by the way, this is Fourier. We're looking at Fourier transform. I think this is Fourier. Let's see. Oops, I went back. If I'm not mistaken, I'm sorry, I keep going back to this guy. Anyway, all these characters are here. I have to look at it in a different way and tell you tomorrow. Not tomorrow, Thursday. So let me wrap up. It's been a long time already. I'm going to take you to the study of all kinds of problematic things now for a while. And all the nice things that I've shown you, which were doable, which you could write out, which you could do Laplace and Fourier and all these crazy, pretty transforms and peek at answers. Pretty much everything will fall by the wayside for a while. And I'll show you the Wild West of nonlinear equations. And from that, come down to which parts of the Wild West we are able to deal with and which parts of the Wild West we are not able to deal with, and what that means in the big picture. All right, let me finish here. I know I've overshot quite a bit, so let's wrap it up. So we'll meet on Thursday, as usual, 2 o'clock. I don't know who's speaking. Do you know who's speaking, Tony, on Thursday?
No.
Colloquium? Okay. I didn't see a name, so all right. So we'll meet on Thursday again. And in the meantime, keep working on the proposal, not the proposal, but the problem itself. Now that we are kind of getting to a point of what the proposal should have looked like, and we can jump to the problem. All right. Bye-bye.
Yep.